For some, winter casts a magic spell. But for others, the freezing season's not too pleasing. Yes, the city is snowbound. Overnight, we were besieged with over 12 inches of the white stuff, and the mayor's office has declared a snow emergency. Every snowplow is out trying to clear the roads, but they just don't seem to be able to get the job done. Fortunately, there's help at hand. What kind of help? An intriguing mathematical pattern called an Euler circuit.
What I wanted you to do right now when I give you the piece of paper, I'd like you to figure this out, this shape, make it in one stroke without picking up your pencil.
It looks as if these students are attempting to solve a simple puzzle. Draw a house without lifting the pencil from the paper or retracing any lines. But that's really the basic concept behind Euler circuits. An Euler circuit is a continuous route through a street network, where you cross over each street only once and return to the starting point without retracing any steps. But how would an Euler circuit help the snowplows? Larry Bodin, professor of management science and statistics at the University of Maryland and president of Distinct Management Consultants, explains.
It would allow each of the plows to work more efficiently. And by working more efficiently means you can do more productive work per hour. And if it can do more productive work per hour, it can get the streets cleaned faster than it could without an Euler circuit in that network.
The idea of Euler circuits was introduced in Königsberg, Prussia, over 250 years ago. A local mathematician, Leonhard Euler, attempted to help the residents find out if there were a way to cross over each of Königsberg's 7 bridges just once and return to any starting point without retracing their steps. Larry Bodin.
In order to study this problem, Euler drew a diagram of the town. He drew a dot to represent each section of land. We call this dot a vertex or node, and lines to represent the bridges. We call these lines edges or arcs. He then looked at this representation, which he called a graph or a network, and this became the first problem in the whole area of mathematics called graph theory or network analysis. What Euler did was he examined this graph that he drew. He found that he could not trace a continuous path that covered all of the edges or arcs in this particular network because at least one of the nodes had an odd number of arcs meeting it.
Why did 3 arcs at a node prevent Euler from finding a circuit?
You cannot do it with 3 arcs for the following reason. The first time you could enter the node along arc 1. Then you could leave along arc 2. The next time you come, you enter the node along the 3rd arc, but you cannot leave because there's no 4th arc to leave on. Therefore, you have to retrace one of the arcs. He then proposed that for a circuit, which then became known as an Euler circuit, to exist in a network, the network had to be connected. You can't have a continuous path if the streets aren't connected. Then there must be an even number of arcs meeting each of the nodes, because when you walk a path and covering every arc once, you have to come in on one arc and leave on another arc.
Okay, so how do we apply Euler's 18th century ideas to the snowbound streets of a 20th century city?
We take a set of streets that make up one route for a snowplow. This makes up a street network. We then abstract it in the way Euler did in terms of representing each intersection as a node and each street segment as an arc. We then examine that network. If each node has an even number of arcs meeting it, then we know that we can find an Euler circuit in that network.
But wait a minute. Most cities just aren't laid out that way. There may be an odd number of streets meeting at an intersection. And it's unlikely that the city is going to create new streets just so the snowplow can have an Euler circuit. So what happens now?
Well, when there's no Euler circuit, the snowplow has to repeat some of the streets, even though the snow has already been removed. We know that repeating some streets is not very efficient, but creating an Euler circuit is. What we're going to have to do is to add additional arcs to the network by repeating some of the arcs in the original network in order to create a new network called a balanced network where every node has an even number of arcs meeting it. Therefore, it satisfies the conditions for an Euler circuit, that is, that the network is connected and that every node has an even number of arcs meeting it.
Since the repeated arcs represent non-productive work, like the snowplow that had to repeat the plowed street, how do mathematicians keep the number or length of these arcs to a minimum? Or in other words, determine the shortest cost? In the early 1960s in China, a mathematician named Miko Guan studied this problem. But it wasn't until the mid-70s that Jack Edmonds of the University of Waterloo in Canada and Ellis Johnson of IBM and Georgia Tech developed a procedure for determining the shortest cost for balancing a graph. So, which are the shortest cost arcs for our snowplow?
Let us consider this graph, and let us assume that this graph represents the required streets in a snowplow route. Most of the nodes in this network have an even number of arcs meeting it. But there are 4 nodes that have 3 arcs meeting it. We now want to create the balanced graph from this graph in order that we can find an Euler circuit in the balanced graph. We have to add a set of arcs to the graph. It can be this set, or this set, or this set. Which one do we choose to repeat? Well, suppose distance is the primary concern for the snowplow route. This set totals 21 miles. This set totals 30 miles. And the final set is only 15 miles. So we want to use the arcs with the least distance or cost. This set of arcs is selected. We now can find an Euler circuit in this balanced graph. If we had been interested in time, we would place a different value in each of the arcs. As you can see, this set totals 10 minutes, so the arcs we choose to repeat for time are different than the arcs we chose to repeat for distance. Take traffic density, again a different value on the arcs, and we choose a different set of arcs. In all 3 cases, the cost of the repeated arcs is a minimum according to the measure that we've used. And we have repeated the arcs so that we can find an Euler circuit in the balanced graph.
But what about real-world problems regardless of weather? Dangerous turns, one-way streets, streets that aren't connected. And how do you plan for an entire city?
We first take into account such factors as the priority streets, direction of the streets, time to accomplish plowing, the time it would take to traverse the street when not plowing, and break the city down into regions. The computer system that we have developed determines which arcs to repeat in order to minimize the total amount of non-productive work. The next time it snows, the computer can not only efficiently route the snowplow crews, it can also determine the fewest number of crews required, with each crew doing the same amount of work. Using math helps the city become more efficient, and hopefully it will never be snowbound again.
For cities, towns, and businesses, computer-generated Euler circuits are used to save time and money in meter reading, street sweeping, and garbage and recycling collection. But you don't need a computer to draw an Euler circuit. Just get out any street map, and with the information you've just seen, you can find the most efficient route for delivering newspapers, for setting up a neighborhood watch, or for many other activities. Who knows? Maybe in the next snowstorm, your city will be calling you.